So here's a population of people that I made up, and it has well, column A is just the ID number of each person, and column B is the height of each person in the population. This goes down to 800 because there's 800 people in here. So it's just showing the height of each of the 800 people. Column C is just random numbers that I created so that I could shuffle these numbers to get random samples. So all we really care about are column A and B, the ID numbers and the heights. This right here is the first 30 rows of the population, meaning the first 30 people in the population, because it goes down to row 30. So this is the height of person 8, this is the height of person 9, going all the way down to row 30 right here. This is the average of the 30 people. So if you added their 30 numbers and divided by 30, you'd get that number. We need to know what the population mean equals, which is what you would get if you added all 800 numbers and divided the total by 800. We can find that out right here. I just have to go down to the bottom. Right here, type in equals average. And actually, if I enter B1 colon B800 and close the parentheses and press enter, it actually gets the average of all 800 numbers in column B, which is all 800 heights. So it just added all 800 of them and divided by 800 to get the population mean. So now we know what the population mean is, the mean of all heights in the population, and also the mean of the 30 people in the sample. But what if I shuffled these around to actually get a random sample of 30 people? I could go data, sort, and then sort by column A. No, actually column C, the random numbers. It'll sort the random numbers from lowest to highest, which will move the rows around. And then now the first 30 people actually are a random sample because these are their ID numbers. So it's 30 randomly selected people. Their mean is 64.26, which is pretty close to the mean of the entire population, because that was, go down here, let's it was 63.7, and this was 64.2, so they're pretty close. So I have one sample of 30 people right here. Since I'm taking a sample size of at least 30, the possible samples that I'm selecting from follow at least roughly a normal curve like this, with the population mean at the center. So the population mean of 63.7, which I calculated, is at the center right here. and then the sample mean was 64.2, which was a little bit higher. So if this is the population mean, the sample mean of 64.2 is about there. It's pretty close. Now if I wanted a different random sample, I could just reshuffle over again. Just have to go all the way down to 800 and then sort by column C. Now this will be another random sample. This time the mean is actually exactly 64, the mean of the sample. 64 is, well, if this was 64.2, then 64 is a little bit to the left. This would be 64. They're both a little bit above the population mean. Now the standard error would be the standard deviation of not just these two sample means, but it would be the standard deviation of all of the means of all possible samples under this curve. Because what this curve is outlining is the sampling distribution of including the means of all possible samples of 30 that could be selected. These were just two samples of 30 that happened to be selected, but this includes all possible samples of 30. And if we wanted to know what that standard deviation would equal, it could be calculated with the standard error formula. It would be the symbol for standard error is sigma x bar, because it's the standard deviation of all sample means, of all possible samples. And we're taking samples of 30 from a population of 800 in this example. So the population is 20 times bigger than the sample, because 30 times 20 would actually be 600, which would mean that the standard error would actually be the short formula. The short formula would give us a pretty good answer, just the population standard deviation over the square root of our sample size. First, we have to find out what our population standard deviation is. We could find it by going here. You have to go to the bottom of the population. Remember, column B has the heights of all population members. This was the mean of the population, the 63.7, which we wrote out right there. If we type in equals stdev.p and type in B1 to be 800, it'll calculate the standard deviation of all 800 heights in the population, and it's about 2.67. So that's our population standard deviation, 2.67, which we got with Excel. And the sample size, the little n, is, well, we're taking a sample of 30, so it's 30. And we can just plug these two numbers in. Now, if we wanted to do it with a long formula, we would also enter in our population size of 800. but that wouldn't affect the answer very much because the population is 20 times bigger than the sample, and we can just use the shortened formula. So it's 2.67 over the square root of 30. First, we need to find out what the square root of 30 is. It's about 5.48 rounded. So we actually want 2.67 divided by the square root of that number, 5.48. .67 divided by 5.48 is about 0.49. So that's our standard error. So all of the sample means under this curve for all possible samples of 30 is 49. The standard deviation of all sample means under this curve is 0.49. And I said what a z-score is the number of standard errors that a certain sample mean falls from the population mean. So let's round our standard error to 0.5. And then what we could show here is that the the sample mean that's 0.5, meaning one standard error below the population mean, would have a z-score of -1. So remember when we talked about the z-scores of individual people, it was the number of standard deviations below the population mean. Now we're talking about the z-score, not the z-score of a person, but the z-score of a sample. The z-score of a sample mean, which is, and when you talk about the z-score of a sample mean, it's actually the number of standard errors that the sample mean is below the population mean or above the population mean. So a sample mean that's 0.5 above the population mean, meaning one standard error above the population mean, would have a z-score of +1, which means since our population mean is 63.7, a sample mean with a z-score of -1 would be 0.5 below this, which would be 63.2. If I took a random sample of 30 people and the sample mean came out to 63.2, my sample mean would have a z-score of -1 because it's one standard error under the population mean. If I took a random sample of 30 and I got a sample mean of 64.2, it would be one standard error above the population mean, which would mean that this sample mean would have a z-score of +1. The z-score of a sample mean actually has a formula. It's the sample mean minus the population mean over the standard error, which is, the standard error is just sigma over square root of n, the short formula for standard error. Now let's find out what the z-scores are for the samples that we actually did select. We can do this pretty easily because we know what the standard error is. We found out that it's about 0.5 doing this work already. So 64 minus our population mean of 63.7 is, well, I mean, we have to divide it by 0.5, which is the standard error. So you have to subtract and then divide. 64 minus 63.7, 0.3 divided by 0.5 is 0.6, positive 0.6, which means that this sample that had the mean of 64 has a z-score of 0.6. Now what about this other sample mean? Well, we could just plug this in where 64 is to get that z-score. 64.2 minus 63.7. And it turns out that we actually did get it turns out that our second sample mean right here actually does have a z-score of exactly 1, because we actually did get a sample mean of 64.2. We actually did get a sample mean that's 1 standard error above the population mean. Now, a sample mean down here below the population mean would have a negative z-score. Like I said, if we got 63.2, the z-score of our sample would be negative 1. It turns out that if the sample means follow a normal curve, then it's actually possible to predict or to calculate the boundary points of the samples of the middle 95% of the possible samples. So let's imagine here that this is the middle 95% of the possible samples, meaning out of all possible samples of 30 that could be selected, 95% of those samples have a sample mean in here. Down here would be the lowest 2.5% of the samples, meaning this would be the samples of 30 that would give the lowest sample means. So these, if I took a sample of 30 from the population and I got a really low sample mean, my sample mean would be down here somewhere. If I took a sample of 30 and got a really high sample mean, my sample mean would be up here somewhere. But if I take a sample of 30 and the sample mean is at least fairly close to the population mean, then my sample mean is in here somewhere in the middle area. So we have a left tail, a middle, and a right tail. Turns out that when the possible samples are normal like this, like they are when the sample size is at least 30, or the population that you're sampling is normal, then 95% of the possible samples fall between the z-score of negative 1.96 and the z-score of positive 1.96, meaning 95% of the possible samples are between 1.96 standard errors below the population mean and 1.96 standard errors above the population mean. Only 2.5% of the possible samples would have sample means past this point, and only 2.5% of the possible samples would have sample means past this point. Remember, under this curve we have not just these two samples of 30, but all the means of all possible samples of 30. And the reason why the curve is so tall over here is because there's lots of samples that have sample means near the population mean. And the reason why the tails are so short is because there aren't that many samples of 30 that would give sample means way down here, and there aren't that many samples of 30 that would give sample means way out here. So these samples have sample means that are really low. These samples have sample means that are really high, and there aren't as many of them because they're more extreme. Now, we could actually calculate the distance from the population mean to the boundary points of the middle 95% of the samples. As long as the possible samples are following a normal curve, like they are here, you can actually calculate this distance. It's called the 95% margin of error. Since we know that 95% of the possible samples are between negative 1.96 and 1.96, we have to somehow turn this z-score into the margin of error that we want. And there's a way to do that. The z-score is this formula right here. Now, we know that the z-score at the boundary up here is 1.96. So we can plug that in right here. And what we actually want to solve for is the top of this formula, the x bar minus mu, because this right here is the distance between the sample mean and the population mean. If we can solve for this right here, what we'll actually get is the distance between the sample mean that's up here at the boundary point, this sample mean, and the population mean at the center. We'll find out how far apart they are. That's this distance right here. So this is actually, since this is the distance between this sample mean at the boundary and the population mean here, this is the 95% margin of error that we need to solve for. The way we can solve for it is by just doing some algebra here. And if you're wondering where the 1 point, how I knew that z-score was 1.96, it comes from a table. Because, like I said, if the sampling distribution is normal, this boundary z-score is always 1.96. So now let's multiply this out. If I multiply both sides by the standard error, this cancels out. This cancels out because of algebra this time. this is on the bottom, and you multiply, it cancels out, and all you're left with is this in the green circle. So it turns out that the 95% margin of error equals the boundary z-score of 1.96 times our standard error. That's our formula for our 95% margin of error. The formula is 1.96 the boundary z-score times the standard error. And we could solve for this because we already know that the standard error over here is 0.5. We calculated it earlier. So our margin of error is just 1.96 times the 0.5. And it is 0.98. So when I'm taking a sample of 30 people from this population over here that I was sampling, and I get the mean of my sample of 30, um, 95% of the possible samples that I could select have sample means that are somewhere between 0.98 below the population mean and 0.98 above the population mean. Because we just found out that our margin of error is 0.98. So this is 0.98. This is also a distance of 0.98. So 95% of the possible samples of 30 would give us a sample mean somewhere between 0.98 below this population mean and 0.98 above that population mean. If we wanted to find out what these boundary points actually are, it would be 63.7 minus the margin of error of 0.98. This boundary is a sample mean of 62.72. This one up here will be 0.98 above the population mean. Which is a sample mean of 64.68. So any sample mean above 64.68 is in the right tail over here. And any sample mean out beyond this other boundary would be in the left tail. It would be in the lowest 2.5% of the possible samples. So any sample mean that's more than 0.98 below the population mean is in the left tail. Any sample mean that's more than 0.98 above the population mean is in the right tail. And well, I think that's good enough for this video. We'll pick up from this point next time.